See, when it comes to coordination compounds, first thing you need to understand are salts are categorized as two kinds. The first of a kind is called addition salt. This is addition salts, and the other one is simple salts. Now, within addition salts, we have two kinds. One is a double salt, the other one is a complex salt. Okay. What do you mean by double salt? These are those addition salts which retain their identity in solid state and lose their identity and form basic constituent of ions in the aqueous state. What does that exactly mean? Suppose if you take any typical double salt like K2SO4 dot Al2SO4 thrice dot some ZH2O. This is how double salts usually are represented. This, let's say in solid state, the minute I add it to aqueous solution, okay, you would notice it will convert into 2K plus aqueous ion, okay. It will convert into 2Al plus 3 aqueous ion, and it will convert into 4SO4 2 minus aqueous ions. So I'm not able to exactly separate out K2SO4 and Al2SO4 because these two are two different salts. Instead of identifying them as salts, we are identifying them as basic constituent ions. Basic constituent ions means these ions cannot be further split into smaller ions. Okay. And next, the example which I have written here, suppose if it was 24H2O, okay, this is called potash alum, one of the very important double salts which you will be learning over time. Now, when salts are given in redox reaction, you must have remember the equivalent weight is equal to molecular weight by valency factor, and valency factor of a salt is the total positive charge or a total negative charge it is carrying. In this case, the total positive of the charge is 3 2s are 6 plus 2 8. That's why the equivalent weight of the double salt here will be molecular weight by 8. Okay. One more salt of a similar kind is ammonium NH4 twice SO4 dot FeSO4 dot 6H2O. If this has been added to aqueous solution, it will convert into NH4 plus Fe plus 2 plus 2SO4 2 minus, all in aqueous solutions, aqueous ions. In such case, the equivalent weight now will be equal to molecular weight by 4, because total charge is 4 here. Okay. The common name for this particular salt is Mohr salt. Again, very, very important salt which we'll be using a lot of times in the topics. So remember what is Mohr salt. All right. Another important salt that you need to remember is KCl MgCl2 dot 6H2O. If this salt is been added to water, it will convert it to K plus Mg2 plus 3 Cl minus, all in aqueous forms. Equivalent weight now will be molecular weight by 3. Okay. The name of this salt is carnallite. Again, during metallurgy, we'll be using this carnallite a lot of times. So please remember this part. Now, when it comes to double salt, the definition suggests that it would be retaining its identity in solid state. That means solid state, we can separate these two and see, okay, there are two different salts, K2SO4 and Al2SO4 thrice. Okay. But the minute you put it in aqueous solution, they all will dissociate into ions now. Got it? So, for example, if I copy this again to explain how the ionization works here. So check. Whatever the K plus ion which is present, in case in this aqueous solution, if I add H2PtCl6, which is called platinic acid, which is colorless solution, it will suddenly start becoming K2PtCl6, a yellow color precipitate, a yellow PPT. A yellow PPT is an indication that there is sufficient amount of potassium ions present here. Similarly, if you have reaction of this solution with NaOH, suppose if I add NaOH, then you might start seeing a white gelatinous precipitate, white gelatinous precipitate, which indicates the existence of aluminum ions. Similarly, if you react the solution with barium chloride aqueous solution, I mean, if you add barium chloride salt to this aqueous solution, then you will end up noticing barium sulfate, a white PPT forming here. Okay. So, and this white PPT is insoluble in dilute HCl. So, if you add dilute HCl also, there will not be any change in this one. While here, if you add dilute HCl, it will get dissolved. So, that's how you can differentiate whether it is about aluminum or barium. So, I hope you got an idea that double salt is something which will get easily ionized in aqueous solution and give you those ions for which the identification uh, test can be seen, and you'll be seeing the basic ions. You'll see the positive test for all the basic ions here. Okay, so I guess all of you understood this part. Please check and write down. Make sure that you have written it. If there is any doubt, you can ask. That right. Now let's understand what are complex salts. These are the ones which will retain their identity both in solid state as well as aqueous state. Okay, they will retain their identity in both aqueous state as well as solid state. For example, FeCl3 is a simple salt. Okay, and when you treat this with KCN, correct, in a liquid state maybe, then first it will convert into FeCN thrice, a precipitate, correct, and that when you add it with excess amount of KCN, if it is excess of KCN here, correct, in that case it will be converting into K3 FeCN6. This is a complex form what you will get. Got it? Now, this, if you solidify or crystallize this part, okay, now using this crystal, K3 FeCN6 crystals, imagine, These crystals, if you add it to aqueous solution, then you would only identify this as 3K plus FeCN6 overall 3 minus. That means even in solid state, it exists as 3K plus ions surrounded by FeCN6 3 minus ions. This is in solid state. Solid state also, it is an ionic crystal which exists as K plus and these ions. And when you add it to aqueous solution also, it is identified in the same manner, right? Which means you're not seeing that the salt is converting into a basic ions like double salt. Which means in case if at all I try to do any conformation test for iron, conformation test for iron is that you react that with potassium thiocyanide and expect that there would be a red color solution forming, blood red coloration. Correct? This is expected. But unfortunately, this is not being successful, which means we are not able to see iron ions in the aqueous solution here. That's why there is no red coloration observed. Okay. Similarly, if you want to check out the existence of only cyanide, okay, if you want to check out the existence of only cyanide, so even when you react this with silver ions here, if it was a cyanide, we should get a white PPT here. Got it? So here, this particular reaction is also coming out to be negative. That means there is no conformation of AgCN forming, which suggests that neither Fe plus 3 nor Cn minus is individually available. This is the way it exists in solid state. It is the same way it exists in the aqueous state. So it will not ionize into smaller ions anymore. So if that does not happen, you call it as a complex salt. Correct? So I hope the basic definition is clear to everyone. Okay. Now within this complex salts, we have two kinds. One is perfect and the other one is imperfect complexes. Okay. Perfect means what? Which perfect. Perfect means what? Which do not give any small constituent ions uh, present in complex form. In the complex form, it will not give anything. Imperfect imperfect means small amount of complex dissociation small amount of complex dissociation is observed. For example, if I take CuCN4 3 minus, this is the complex form or the complex part. If this complex part on treatment with H2S vapors, correct? H2S vapors are being sent. If by chance, if this complex has the copper plus ions present to a smaller extent also, we should be able to get this kind of, precipitate. But this precipitate is not forming, correct? This precipitate is not being observed. Okay. Similarly, if I take FeCN6 overall 3 minus and I treat this with KSCN, here also I'm expected to get this as SCCN thrice, blood red coloration, correct? Here it is a black PPT. Neither this reaction or not this reaction is successful, correct? Now, this can also attribute to its high Kf value. What is this Kf and K? Instability constant. Let me explain. If I take copper plus 4 moles of cyanide, it will convert into CuCN 4 times 3 minus. The equilibrium constant for this is usually called as formation constant. And the formation constant in the case of copper is approximately 4.5 into 10 raised to power of, sorry, 9. 9 into 10 raised to power of 27. Got it? 9 into 10 raised to power of 27. So can you see that means it is almost the reaction is in the forward direction. Or approximately, if you notice the K instantaneous value here, so that is about 1 by 9 into 10 raised to power of minus 27. Got it? Instability, this is called instability constant. That means the backward ionization. Okay? Forward complex formation. Kf is forward complex formation. K inst means ionization. So you can notice that the ionization constant is extremely low, which means you will not have any sufficient concentration of these two available to get any of their confirmatory test. Such kind of complexes are called perfect complexes. Hence, you can notice this is a perfect complex. This is also a perfect complex. Now, what are imperfect ones? See, if you take cadmium CN4 overall 2 minus, and that if you pass it to H2S, got it? Then you would actually see a yellow color precipitate forming, yellow PPT forming, got it? Which means this yellow PPT is attributed to the small amount of dissociation of cadmium 2 plus and cyanide. So, of course, the equilibrium still lies on the backward direction, but yet the K instability constant this time, if you compare it, is 4 into 10 raised to power of minus 7, which is not that bad. That means there is small composition of cadmium 2 plus and cyanide minus will be present, and it is showcasing that if you are treating this with H2S, we are able to get that into CDS precipitate formation. Hence, this will be an imperfect complex. Imperfect complex. Correct? Few more, if you notice, ammonium, silver ammonium complex. Silver ammonium complex also, if you treat with H2S, it will start forming Ag2S, a black PPT. Alright. Similarly, if you take nickel ammonium complex, NiNH3 6 times 2 plus, if you treat this with H2S, this will also give you a black PPT of nickel sulfide. This suggests that these are all imperfect complexes. This is also an imperfect complex. This is also an imperfect complex. Got it? So I hope all of you understood the difference. What is perfect and imperfect? Okay, please check it out quickly. If you want to check the definition of complex also, just go ahead from the top, from here to here. Make sure you're complete writing also. Finished? Right. Now let's get into this. What is the nomenclature that is used in complexes? Basic terms. What are the basic terms that are used in our complexes? So let me write the complex. Suppose there is a small part which is outside, and then there is a part which is inside, like this. This is how the general complex representation looks like. Okay. This has been divided into like two parts. The outside part is called, ionic sphere. The inside part is called as the complex sphere. Okay. These are the two terms that have been used. So this is ionization sphere, ionization sphere, and this part is coordination sphere, coordination sphere. Okay. And the metal which is at the center, that is termed as central metal atom. Henceforth, you will use this as CMA. And the ligands which are present, those are called as simply these groups which are present are called as ligands. Okay. And the X present in it is called as the coordination number. Coordination number. Okay. Clear? So I guess this part is clear. So the entire bracket is what we call it as the coordination sphere. Anything outside is what we call it as the ionization sphere. And the metal which is present at the center is called the central metal atom. And L which is present are called as ligands. Okay. For example, if you have K3FeCN6. Okay. So you can relate this is, you know, outside ions, ionization sphere. Got it? This is central metal atom, and this is ligand, and this 6 is coordination number. Got it? Just a second. Right. So check. These are Lewis bases and electron pair donors. Ligands are basically Lewis bases, which means they are ready to donate a pair of electrons. While central metal atom is the Lewis acid, which is accepting a pair of electrons. So, which means the bond between these two, right? So, if you notice the bond between ligands here, so ligand and CMA bond, correct, is in a way coordinate covalent bond. Coordinate covalent bond. Got it? How do we represent that? Typically, this is how we represent that there is central atom and there are 6 coordinate covalent bonds observed from 6 cyanides towards iron. So iron is ready to accept 6 coordinate covalent bonds, and overall it has 3 minus charge on it. This is the way. Second thing, the bond between the ionization sphere and coordination sphere is purely ionic bonds. So this bonds between the spheres is ionic bond, correct? So suppose if I have given you this question that how many number of what are the different types of bonds that are present in a complex like K3 Fe here? Let's say K3 Fe CN6. Correct? How many different type of bonds present? Different bonds present. Then what do we check? We know that there is ionic bond present, which is correct. There is coordinate covalent bond present, which is also correct. Then there is covalent bond present. That is also correct. Why? Between carbon and nitrogen, we have covalent bonds only. So therefore, we have ionic, covalent, and coordination covalent bond also. Clear? So I hope the basic terms are clear, everybody. Then check. See, coordination number, particularly we need to discuss, uh, because we have coordination number varying depending upon the type of ligand that we use. For example, if I take cobalt H2O 6 overall 3 plus, then the number of ligands, in this case are 6, and coordination number is also 6. Now, what is the difference between these two? Basically, coordination number represents how many electron pairs are accepted by central metal atom. So here central metal atom is accepting total 6. So that is why the coordination number is 6. But if the same compound is being connected with another ligand known as En, in the case of En, now the number of ligands are 3, but coordination number is still 6. Coordination number is still 6. Why is that so? See that cobalt here is connected with 6 water molecules in coordinate bond form here. So water is being surrounded from all the ends like this. While here, in the second case, here also we have 6 connections. Here also we have 6 connections, but these 6 are coming from nitrogen ends of the molecule like this. This is the molecule which we are talking about. This is called ethylene. En is ethylene diamine. And each molecule gives 2 connections. So coordination number is 6, but the number of ligands are only 3 here. Okay. Yes, beta. Any doubt? Here the coordination number is 6 because there are 6 connections to the central metal atom, but they are all coming from only 3 ligands. Each ligand is offering 2 connections. Got it? So that's the difference between coordination number. I mean, that's the difference between number of ligands and coordination number. So if a ligand is only giving one connection, we call it as monodentate ligand. If they are giving 2 connections at a time, we call it as bidentate ligands, right? So anything which gives n number of connections, we call it as polydentate ligands. Anything more than one connection is always called as polydentate ligands. All right. So it becomes very essential to understand what are the types of ligands we are talking about. So these are the basic definitions. Again, I gave it. So coordination number, central metal atom, complex, and what is coordination number. Now, one thing you need to remember here is that there are metals which significantly check out only for one type of coordination number, which means if it comes to copper plus, usually it will either make a coordination number 2 or 4. You do not often see a complex having 3 ligands or 3 connections with copper 2 plus or 5 connections with copper 2 plus. Similarly, when it comes to Ag plus, you'll always see only 2 connections. Au plus 2 or 4, Hg2 plus only 2, but Hg2 plus will give 4. Copper 2 plus will offer 4 and 6. Ag2 plus will always have only 4. Pt2 plus will have 4. Pd2 plus will have 4. Mg2 plus will have 6. Correct? If it is Pt plus 4, it can go to 6. Cobalt plus 3 always offers 6. Cobalt plus 2 offers 4 and 6. Iron plus 3 always have 6 coordination number, plus 2 will have 4 and 6. Nickel plus 2 will have 4 and 6. And these are very, very common metals which have forming maximum complexes. That's why this list of coordination numbers is important for us. Okay, next. Check. How do we classify these ligands? Okay, ligands can be classified on the basis of, charge they are carrying, on the basis of bonds they are making, on the basis of number of connections they are making. So depending upon different classifications, we will see it. The first classification is based on charge. Based on charge, ligands can give you, there are in fact three types of ligands. One is positively charged ligand, negatively charged ligand, and neutral ligand. Positively charged ligand, negatively charged ligand, and neutral ligand. Let's see positively charged ligand here. Okay, you hardly have any ligands which are actually positively charged, and yet they are giving a coordinate. I mean, yet they are acting like a base. Very less compounds like that. One of them being NO, NO plus. This will have a lone pair on nitrogen end here, right? Structure wise, it is N double bond O plus with a lone pair on nitrogen. This is called as nitrosyl. Nitrosyl is the compound name. The minute it becomes plus, whenever there is a plus, you'll always end up giving a suffix ium, em. So it is a nitrosylium, uh, nitrosylium ligand. Next, if you have NH2 and the other side we have NH3 plus. Basically, NH2 is hydrazine. Now, because we got NH3 plus, NH3 got a plus charge. Now it is becoming a positively charged ligand, but it is still ready to give away one lone pair from the other nitrogen end. So this is called hydrazinium hydrazinium ligand. Again, you can see ion here, IEM, ion. Okay, so like this, if you have H3O plus, H3O plus, if it is offering one uh, compound here, so this is hydronium, hydronium. Okay, these are typically positively charged ligands, which you will see, which have still one lone pair at least on them, which can be offered as a base to central metal atom. Next, negatively charged ligand. Check out on negatively charged ligand. That is, in negatively charged ligand, you remember it like this. If you have any ide-ended salts, that means salt ions, which are ended with ide suffix, then you have to make it into ido while writing the ligands. Okay, got it? So ide will become ido. Now, this is as per new IUPAC naming. In old IUPAC naming, it was simply the ide was written as simply O. So this is old IUPAC naming. For example, if you have Cl minus, okay, earlier the ligand was named as chloro. Okay, this is as per old IUPAC name. The new IUPAC name is chlorido. So this is as per new IUPAC naming. We follow both, but first priority is always given to the new one. Okay, so chloro. So Cl minus is written as either chloro or chlorido. Now, which of the compounds which we know are ide salts? See, any salt which is forming from ic acid, correct? Hydrochloric acid, hydrobromic acid, hydrocyanic acid, right? And hydrosulfuric acid. Okay. So if at all you have an ic acid, ic acid, and it is directly connected to central atom, correct? So then that is called as an ic acid, and all the ic acids are converted when they are in the salt form. You call it as ide salt. Sodium chloride, sodium bromide, sodium fluoride, sodium cyanide, sodium phosphide, sodium sulfide, correct? So that will become ide salts, isn't it? So those ides, when you write it as a ligand, then what is the name that you will write it here? So for example, if you have Br minus, we'll be writing this as bromo, old name, or bromido, new name. I minus, we write it as ido, okay, or the new name is idido, okay, clear? Or if you have cyanide, Cn minus, it will become cyano or cyanido, okay. Next, if you have N overall 3 minus, this is nitride. So this will become nitrido. S2 minus, that will become sulfido. It is sulfide, so it will become sulfido. If N3 with overall minus is present, this is coming from a salt called azide. So it will become azido. Okay, that will become azido. Clear? Even OH minus is called as hydroxide. So it will become hydroxido. Okay, or commonly it is also known as hydroxo. Okay, hydroxo. Similarly, O2 minus is also an oxide, so that will become oxido, or simply we use it as oxo. If you write it as O2 2 minus, that will become peroxide, so it is peroxo. Okay, peroxido, or simply peroxo. And if you have O2 overall only one minus, that is superoxide, superoxido, or superoxo. Especially in the case of oxides, common name are very often used. So it is oxo, peroxo, superoxo is used. Okay, right. So similarly, just like cyanide, we can have Cn minus, SCN minus, so that will become thiocyanide, thiocyanide. Correct. So I hope you got a clarity on that. If you have negatively charged, how many different types of names we can get. So these are all ide salts converting into ido. Okay. Next. Next one is eight salts. Check out eight. Eight salts, you have to write it as atto. And eight salts, you have to write it as ito. This is the conversion that you need to do it. For example, when do we get eight? Sulfate, carbonate, oxalate, carboxylate, correct? Nitrate, eight. Higher oxidation states, we always get this as eight. So that's why the naming, if you have sulfate as a ligand, so sulfate, which is SO4 2 minus, that is sulfate. Now what will that become? Sulfato. Got it? Similarly, NO3 minus, nitrate. So that will now become nitrato. Nitrato. C2O4 2 minus, oxalate. The abbreviation of oxalate is OX. That will become oxalato. Got it? CO3 2 minus, carbonate. So carbonato. Okay. Formate, HCO minus, formic acid becoming formate. So this will formato. Got it? CH3 COO minus, acetate, acetato. Got it? So have you got the rhythm of it? Like, in which case, what is the name that is to be used? Okay. Few more important ones which you need to know is S2O3 2 minus, which is thiosulfato. Thiosulfato. Correct? The other one is OCN minus. So that is cynato, cynato, because this is called cynate. Okay. So if it is NCS minus, sorry, NCO minus, that means the connection is from the nitrogen. So it is isocyanato, isocyanato. Clear, everybody? This is the name that you will come across. Now look into the case where you have ide salts. The ide salts include uh, chlorito, correct? So when do we use that? For ClO minus. ClO minus is basically coming from hypochlorite. So that will become hypochlorito. So ClO2 minus, this is chloride. So simply chlorito. So that will become chlorito. Correct. And if you have NO2 minus, that will become nitrite. So that will become nitrito. Then we have SO32 minus, sulfito. This will become sulfito. Everyone, look into the names quickly. If there is any doubt, you can ask. Or if you are curious to know anything else, you can ask. Now. Chromate, CrO4 2 minus. So what do you write? Chromito, chromato. Manganate, manganeto. Okay, like that you can write it for anything. I hope all of you have finished writing. See, next one. Neutral ligands. Neutral ligands where there is no charge on them. So in that case, we generally use common names. For example, H2O. H2O, you simply use it as aqua. NH3, we use it as amine. AMMINE, amine. Okay. Next we have CH3, NH2, right? CH3, NH2. This is written as methylamine. Mind you, very important part here is it is only the ammonia which gets this double M. Rest all amines are simply single M. Okay, so that level of detailing is important. Next, when it comes to carbon monoxide, it is carbonyl. Carbonyl. Nitro NO also exists only as neutral. That then it is called as nitrosyl. The minute it becomes plus, it will become nitrosilium. Okay. Likewise, if you have pyridine, right, like this, we have pyridine, nitrogen has a lone pair on it. So this is called simply pyridine, or we also use it as pyridyl. Pyridyl. Got it? Like that, if you have CH2, CH2 connected with NH2 and NH2 like this. Okay, so this is also neutral, no charge on it. Correct? It is read as ethylene diamine. Ethylene diamine. And because it is bigger in size and to represent, we use a short form En. So En means ethylene diamine. It will give two connections and it is neutral. Correct? So you must have got an idea that when it comes to ligands which are neutral, we typically have only common names used. Done? I hope all of you got that. See the next classification. The next classification of ligands is based on denticity. Denticity is number of connections they can offer, right? So how many electron pairs they can donate. So check out. So when it comes to denticity, we have monodentates, we have bidentates, flexidentates, ambidentates, polydentates. So all of these forms. So let's see one by one. Monodentates. Monodentates means only single, sorry, uh, one electron pair connection. Okay. Lot of examples, everything that could be neutral like Cn minus, X minus, OH minus. Okay. Ammonia, correct. Pyridine. Pyridine is also written as Py. O2 minus, O22 minus, they all will only offer single connections. OCN minus, SCN minus, carbon monoxide, water, OH minus, right? And NO plus. So all of this, whatever we have studied so far, where there is only single connection or single electron that is being offered, they all are monodentates. Next, let us see what is flexidentate. Flexidentate means it can offer one electron pair or more than one electron pair, okay, as per CMA's need. So if the central metal atom requires two pairs, it will provide two. If it requires only one pair, it will require it will donate only one pair. For example, carbonate CO3 2 minus. CO3 2 minus in some cases acts like monodentate. Monodentate means you can see C double bond O, O minus and O minus. From here, it will connect it to metal. So in some cases, it can offer bidentate also. That means it can give two connections at a time. So that is O, C double bond O, O minus and O minus. But this time metal is expecting that there should be two bonds donating from here. So that means in some cases it is acting like a monodentate, in some cases it is acting like a bidentate. Now, when these kind of situations usually observe when the oxides are strongly resonance stabilized. So that is carbonate, sulfate, sulfite, okay, nitrate, nitrate or nitrito, okay, uh, this oxalate, C2O42 minus, and anything else, S2O32 minus, got it, thiosulfate. So these are all some examples which they offer flexidenticity. Got it? Next is bidentates. Okay. Please make sure that meanwhile you have completed the note. Just a second. So I hope all of you got that. Look into bidentates. Bidentates means it should give two connections. Okay. So you see, starting with ethylene, I would request please write simultaneously because bidentates are a large collection of ligands here. So please learn that and write it simultaneously. En we just learned it is ethylene diamine. Ethylene diamine. So it will have CH2, CH2 with NH2 and NH2. Okay. connected with M. So from metal, this is how it is connected. Okay. So we will also represent from which ends the donors are coming from. You see, in this case, both are nitrogen ends. So we see it as N comma N donors. So both of them are coming from the lone pairs of nitrogen. Correct? Both the connections are coming from that. Oxalate, the abbreviation is OX. So this is oxalato. Oxalato. So it is C2O4 2 minus, but we generally write it as OX. So C double bond O connected with C double bond O, O minus and O minus, that is connected with metal. So the donor sides are oxygen and oxygen. Both ends are oxygen. Got it? Similarly, GLY, okay, GLY is glycinato. Again, very, very important one. You should definitely know the name properly. All right. So glycinato is one of the amino acids. So the structure would be like this. We have CH2 connected with C double bond O, O minus, and this side it is connected with NH2. So if there is a metal, the connection is one from oxygen, one from nitrogen. Okay, so that means it is O and N connection. This is glycine atom. Okay, next one is DMG, most important one. This is the most important one. In fact, these both are very frequently asked, but please do remember DMG is the one which will be asked a lot of times. So dimethyl dimethyl glyoxymeto, dimethyl glyoxymeto. If you notice the preparation wise, basically it is ketones reacting with 2 moles of uh, hydroxylamine to form double bond N, double bond N, OH and OH. And if this is being kept in a basic medium, it will start gaining into NO minus, and the other side it will have OH. At least till the first dissociation, this is when we call it as DMG. This is how we get the DMG part. Clear? And if you notice the DMG, how is the connection here? So we'll have double bond N here, double bond N here. It has O minus and OH. But listen up, the nitrogen is always a better donor as compared to oxygen here. See, for one reason that oxygen are resonance stabilized like this. Here also oxygens are resonance stabilized like this. So nitrogen is more available for connections. And generally also nitrogen is always better donor than oxygen. That's why the connections or the donor side here are N and N and not N and O or O and O. Okay. So this is dimethyl glyoxymeto. Keep that in mind. The next one is BPY. BPY is bipyridyl. Bipyridyl. That means two pyridines connected with each other like this. We have a nitrogen here and another nitrogen here like this, and that connected to metals like this. Okay. So dipyridyl. Again, connection is from N comma N. Got it? Next. Now, these are the ones which are mainly asked for advanced, but you should definitely know the naming for it. So PN, BN, PN, BN, TN. Okay, then oxime. Please remember it this way: PN, BN, TN, oxime. So first one is propyl, propylene diamine. Propylene diamine. This is butylene diamine. Butylene diamine. This is trimethylene. Trimethylene diamine. So that means all of them are diamine. Just the representation, I mean, they are all isomers. Some of them are isomers, some of them are like just the representation differences. For example, here it is about propane having NH2 on one position and two position, and that is connected to metal like this. Okay. This is propylene diamine. Butylene is having four methyls here, NH2 and NH2 this way connected to metal. So it is like ethylene diamine, but two extra carbons here. Next, you can see dimethylene diamine in this case is you have CH2 which have connection with NH2 and NH2, and then we have a metal, so that connects from these two nitrogen ends like this. So you can see the connections in all of them donor sites are N and N, N and N, and also N comma N. This is PN, BN, TN. Okay, remember the abbreviation form. Got it? Oxime. Oxime is 8 hydroxy, 8 hydroxy quinol, quinodino, quinodino, quinodine. So dine will become dino. Okay. So here basically there is a pyridine which is connected with phenoxide ion. So if a metal is connected here from oxygen and nitrogen end, that means N comma O, that is 8 hydroxyquinidino. Okay. So please do check all the names quickly. Okay. All the bidentate forms. These are all very important bidentates, guys. So that much is enough. Check out tridentate now. When it comes to tridentate, there are only two which are very commonly used. The first one is di-N. Di-N is diethylene, diethylene uh, triamine. Diethylene triamine. That means we have uh, two amines at a time. So CH2, CH2, and then we have N and NH2 here. And this NH is again connected to CH2, CH2, and again NH2. So when we have a metal, one connection comes from this nitrogen end, one will come from this nitrogen end, and the other one will come from this nitrogen end. Okay, that's how the connections will be. So connections are N comma N comma N. Okay, the other one is IMDA. IMDA, that is imido. Okay, sorry, imino, imino diacetato. Imino diacetato. Imine is when you have two valency, that means NH, and then you have two connections here like this. So I have C double bond O, O minus, and here also I have C double bond O, O minus. And imagine there is a metal here. So that metal is surrounded by this oxygen, and this nitrogen. So the donor sites are N comma O comma N. This is imino diacetato. Clear, guys? We have acetate group. CH3COO minus is an acetate group. So there are two acetate groups here. Okay. Next, tetradentate. Tetradentase is just extension of what we did here. See, we did it as di-N. Now we'll make it as tri-N. So now the next one is tri-N. Tri-N means trimethyl. Okay, trimethylene, correct? Tetraamine. Trimethylene tetraamine. Okay, sorry, triethylene. We are continuing with the same ethylene. Triethylene tetraamine. So which means I have CH2, and then connected with N. Again CH2, then connected with N. Okay, and I have one more CH2, then connected with N. NH2. Here it is NH2. This way. So now if you have a metal here, so one connection starts from here, one would come from here, one would be coming from this end, the other one will come from this end. So that's how it will act like a tetradentate. Got it? Four connections at a time. Similarly, other one which is used here is NTA. NTA is easy to remember, I'm sure. Correct? NTA 3 minus. NTA is nitrilo triacetato. Nitrilo triacetato. That means now nitrogen has all three connections. Okay, nitrogen with acetate groups. So double bond O, O minus. Here also we have double bond O, O minus, double bond O, O minus, and then there is a metal here. So one connection come from here, the one will come from here, one will come from here, the other one will come from this end, like this. This is the way you will get the connections. So in the first case here, when you have tri-N, all four donor sites are nitrogen. Here one is nitrogen, the other three are oxygens. This is N3A minus. Got it? So this is tetradentates. Okay. So please check what is tridentate and tetradentates. Okay. Next one is hexadentate. Hexadentate is if you have EDTA. In fact, there are many more, but this is the most used one, which is there for a syllabus. And out of all the ligands, I would rate this as the most important ligand, EDTA. Okay. By name, it is ethylene diamine and tetraacetate, acetato, tetraacetate or acetatone. Okay. So imagine we have ethylene diamine. So this is ethylene diamine. And now there is, imagine, metal somewhere here, and it has six connections coming across. So how are the six connections coming? Let's say one connection is coming from here, one is coming from here, and let's say one is coming from here, one connection is coming from here, one is coming from here, and the other one is coming from here, like this. Okay. So which means here the connection is carbon CH2, one CH2 here, double bond, sorry, CH2 with double bond O and O minus. That's how it is connected. See, the other one is also double bond O and double bond O and O minus here. Similarly, we have one double bond O and one O minus. And here also we have one double bond O here, sorry, CH2 here, like this, with double bond O and O minus. Okay. So you could see there are four acetate groups connected to two nitrogen. This you have to practice a lot of times. Please learn to write the structure thoroughly. Okay. So you can see the ligand connections, donor sites are N comma N, and rest all are coming from oxygen. Rest four are coming from oxygen. So this is ethylene diamine tetraacetate. Notice one thing, how many number of N, M and O bonds are there? Okay, if you notice the bonds here, N, M, O. This if I read it as one bond, then we have one here, correct? And then we have one on this end, one we have it on this end, one we have it on this end. That means each nitrogen is making four such bonds, correct? So each nitrogen is making four such bonds here. Okay. So if four such bonds are being made here, so we will have this as total of eight bonds. NMO bonds would be eight. Got it? Similarly, how about we have OMO bonds here? If it comes to OMO bonds here, just a minute. Right. This is about hexadentate form. Next. Check out the special ligands. Okay. Special ligands. Mainly the special ligand which we'll be using is ACAC. Sorry, ACAC. Okay. ACAC is an abbreviation for, okay, acetyl acetonato. Acetyl acetonato. Okay. Basically, it is formed from this active methylene diketone. So if you have a diketone here like this, you know that this part is acetyl, okay, and this entire part is acetone. So acetyl is connected to acetone. That's why it is called acetyl acetonato. Okay. Now you know that this in basic medium will have uh, an enolate form as O minus, double bond with double bond O here, and CH3. Sorry, minus 3. OH here. So we will have this as OH here and this way, so that it can have hydrogen bonding. Correct? This is how it exists. This is the enol form which you have. Okay. Now, when you write this enol form, this is acetyl acetone. Now, if that, if you convert into an ligand, that means you remove out that H plus. The minute you remove this H plus away, now that will turn into a ligand form. So then we read it as acetyl acetonato. Okay. And you see when it comes to acetyl acetonato, as it makes a bond with a metal here, correct? Metal would have connections from this oxygen end and oxygen end. So it is a connection of O and O, acetyl acetonato. Next, let's see what is the idea about the ring formation. Have you noticed something? Except for the monodentates, if you take bidentates, tridentates, tetradentates, hexadentates, pentadentates, anything you take, they are all making us, four membered, five membered, six membered rings with the metal, isn't it? Now let's go back and check. For example, if you take AC and AC, this is one, two, three, four, five, six. That makes a six membered ring. Go back here. When it comes to this metal here, one, two, three, four, five. You can see a five membered ring. Again, one, two, three, four, five. Again, a five membered ring. Here, you can see one, two, three. Sorry, this side. One, two, three, four, five. Again, a five membered ring. So either a five membered ring, a six membered ring are most, entertaining. So you would notice that in most cases, whenever there is a ring formation, and that happens often with polydentates. That could be bidentate, tridentate, or any of them. So during a polydentate presence, I mean, when there is a polydentate present across the central metal atom, so it is evident that they will definitely go for chelation. Chelation means ring formation. So that's why there is a ring formation observed. And what is the importance? Because of the ring formation, now metal is almost masked from any other external reagents. And because it is masked from external reagents, it's difficult to get a connection with the central metal for an external reagent. Hence, that complex remains more stable. And that's the reason why you will see minimum denticity for the ring is 2, and they often form three three-membered, five-membered, or six-membered ring formations here. Okay. So here you can see there are, okay. So there are three five-membered rings present in this case. Okay. You can see complexes are very stable when chelation takes place here. Got it? Complexes are generally very stable when the chelation takes place here. Okay. One of the important compound as it is, which we need to learn, is nickel DMG, which is used as a very important reference of stability of complexes. Like it is always scaled that with respect to nickel DMG, how much is the other complexes are being more stable or less stable. So nickel DMG is a rosy red color complex. Some books give it as cherry red also, that is still okay. Cherry red or rosy red color complex. How does it look like? So nickel would have actually four connections like this. One connection from here, one connection from here, one connection from here, and one connection from here. Let's see. And these four connections are actually coming from nitrogen ends only. And they are coming from this double bond and double bond like this, double bond and double bond here, because we remember the DMG how it happens. Okay. Okay. How it usually come across. Okay. So if you have this connection here, this nitrogen is still connected to O minus here. Okay. And here it is connected to O and H here. Okay. O and H here. So here it is connected as O minus. Here also it is connected as O and H here. So what is happening here is this oxygen is also making a hydrogen bond here. This oxygen is also making a hydrogen bond here. Okay. Because of which now if you see the ring size, this side it is a five-membered ring. This side it is a five-membered ring. And due to hydrogen bonding, this side it is a six-membered ring. This side also it is a six-membered ring. So you can see actually there are two five-membered rings and there are two six-membered rings forming. So two five-membered rings and two six-membered rings observed. Okay. And this is very high Kf value because of its high stability due to chelation. The Kf value is very stable and very stable complex. Okay, so this is something which you need to learn from a chelation part. Got it? So due to chelation, there is large stability that is observed, and more the number of rings you get, more is the stability that you observe. So nickel is extremely masked. So when it comes to nickel, this is extremely masked from the outside ligands. Okay, right. Please do check quickly. Ambidentate ligands. Let's talk about ambidentate ligands. See, if there are two different sites, but at a time only one donor is active, That means both of them are not acting like a bidentate, but only one donor site is active. Then we call it as ambidentate ligands. Okay. For example, Cn minus. Cn minus, structurally it has C triple bond N, lone pair here with minus and one lone pair here, which means it could be acted as two ways here. So if it is connecting from nitrogen end, we read this as isocyano or cyanido complex. If the same thing is happening from the other end here, correct, when it is making one metal connection this way, then we call it as cyanido. So you can see, but both of them are not happening simultaneously, either this or that. So that's when you call it as ambidentate ligands. So you can see, if you have NO2 minus, structurally it is N with a lone pair, double bond O, O minus. So connections can come from this end also, it can come from this end also. Likewise, if you have OCN minus, OCN minus, structurally we have O, double bond C, single bond N, sorry, double bond N with minus here. So that means because of the lone pair present here, it can donate it from this end also, or it can donate it from this end also. Okay. Few more SCN minus. In SCN minus, sulfur connected with triple bond N. This has a lone pair. In fact, sulfur has a lone pair also. So connection can happen from sulfur and also from nitrogen end. Got it? S2O3 2 minus. See, S2O3 2 minus is one such exception where it can act like a flexidentate. In some areas, very less areas, it will act like a ligands here. So otherwise, it can actually give a connection from oxygen end or a sulfur end like this. Okay. Another example is SO3 2 minus. Got it. So sulfur also has a lone pair with a double bond O, O minus and O minus. So you can see it can offer from sulfur end or oxygen end, but both does not happen simultaneously. Right? If it is happening simultaneously, everybody, then you use the word flexidentate. Okay, so you can see these two are those kind of cases where they are offering a flexidenticity as well as they are acting like an ambidentate ligands. Clear on that? Right? So these are ambidentate forms. Now we have learned two classifications so far. One classification is based on the charge for ligands. Second classification of ligands is based on denticity. Now let's see the third classification. This time it is based on what type of a donation the ligand is making. Okay. For example, if you have a donation happening to two different metals, that means ligand is offering, connections to two different metals at a time, then those are called as bridged ligands. That is called as bridge ligands. For example, Al2Cl6. It is a complex where you have, you know, two covalent bonds and two ends here like this with two aluminiums. And then there are two chlorines at the center where they do have a simple covalent bond, and the other end it is making a complex coordinate covalent bond. Here it is making a complex coordinate bond and like this, which means you can see this chloride and this chloride are actually providing connections to two different metals. Okay, so then we call it as bridged ligands. So this is bridged ligand. Okay, usually whenever you have a bridge ligand, we always read it as mu dichloro. Okay, mu comma mu dichloro. That mu is a representation. During IUPAC we learned that whenever there is a mu coming, that means it is in the bridge positions. Okay. Similarly, another such example is when you have a palladium connected with two OH groups here like this, OH and OH here, PD, palladium. Here we have PD like this. Okay. So now again this OH group and this OH group, this is a hydroxide, and but this hydroxide is acting like a ligand. So we write it as mu, comma mu dihydroxo, dihydroxo. These are the donor forms. Okay. So usually the one which we have to act like a bridged ligands, to act like a bridged ligands, they must have at least two lone pairs to donate, right? On both ends. So we have something like OH minus, O2, O2 2 minus. It could be a peroxide. It could be a superoxide. It could be a simple oxide. It could be an amide, NH2 minus. Okay, it could be carbon monoxide also. Carbon monoxide also donates, not necessarily with two lone pairs. It will be one lone pair and one pi bond also. So that's a very different case here. And halogens, etc. These are the ones which typically give bridge ligand cases. Okay, integer type questions will be asked here. So learn to know how to select the options. Either you check out multiple lone pairs or one lone pair and one pi bond present on it. Such cases will give you bridge ligand positions. Second, a ligand which is typically making a sigma donation only. That means it is only giving sigma bonds. Okay, sigma bond as in this case, a coordinate covalent bond is also a sigma bond. That means it is only giving one lone pair electron and has no vacant orbitals. That means it must not have any other vacant orbitals. Got it? For example, ligand to metal, only this one coordinate covalent bond, which is a sigma bond. Examples, if you notice, ammonia, correct? Only one lone pair present and no empty orbitals on nitrogen. H2O, okay, sorry, not H2O, H minus, okay, or any ammonia derivatives also like this, ethylene diamine type. So these are all sigma donors. These all are sigma donors, correct? So only one lone pair and no empty orbitals present on them. Then we have pi donors. Pi donors are the case where you have two or more than two donor sites. That means they are making a sigma bond as well as pi bond also at a time. Like ligand is first making a sigma bond and also it is making one more bond like this. So one will be sigma, one will be pi. Now here there are two cases. One is weak pi donors. That means they are donating, but they are weak in nature to give it, like water, like alcohol, okay, ethers, and so on. That is oxygen connected groups. Strong, strong pi donors are the ones which have charge on it because if they have charge, chances are more to donate. OH minus, X minus, O2 minus, like this. These are all charged pi donors. Got it? Typically, in a um, orbital overlapping wise, if you notice, this is how, let's say, a ligand is making a sigma bond here, correct? And then probably there are some empty pi orbitals here. This is one empty d orbital, sorry. There are some empty d orbital here, correct? To which the pi bond, the lone pair present on this ligand, is trying to make a pi bond with that empty d orbitals here like this way. Okay. You know that typically a d orbital means you'll have four lobes like this. So this is one d orbital. Okay. So such type of d orbital if it is making. So this is how the connection takes place. Okay, beta. So please go through this quickly. What are bridged sigma and pi donors? See, the next type is very important one. That is pi acid or pi acceptor donor. Okay. Now instead of pi, you know, uh, sorry, pi donor, it is now pi acceptor. Okay. So it is not donating, rather it is accepting now. Okay. You see, these ligands have vacant pi star orbital or either d orbitals, which can accept a pair of electrons from metal. Okay. Awesome. Great job. Check out. How does it happen? Look into it. So, what are the pi acceptors if you notice? Acceptors, that includes carbon monoxide, cyanide, CH2, CH2, ethylene, even a simple benzene, correct? Or a pyridine, correct? This case, PPH thrice, PPH thrice, PF3, okay? PCH3 thrice, correct? ASF5, correct? ASF3, sorry, ASF3, okay? Or any arsenic alkyl group, R3, like this. These kind of ligands are pi acceptor ligands. So notice one thing carefully in these cases. Either they have a pi bond along with a lone pair, like carbon monoxide has a lone pair as well as a pi bond. Same goes with cyanide, lone pair as well as a pi bond. Here you have no lone pair but only one pi bond. That means either you should have one lone pair and one pi bond or only pi bonds. Correct? Second cases. Notice this one. If you notice this cases PPH thrice, PF3, PCH3, and ASF5, and all of this, they have a lone pair as well as an empty d orbitals. So this is a condition. Either you should have an empty d orbital to accept. Now, structure-wise, if you notice, we have a metal. Now, imagine in a lot of cases, metals d orbital might also have a pair of electrons. Okay, and on one end, it is making a sigma bond with the ligand like this, and ligand has empty orbital on it. Ligand has an empty orbital here, so this is empty empty pi star orbital here. So it will have an empty pi star orbital, or it could be, sorry, or it could be empty d orbital, any one of that, empty d. And now how does the bond happens? From here to here, the electrons might be moving. So that means this is a kind of donation which you will notice like this. And here sigma is donating towards this end, correct? That means ligand is donating from this end and d orbitals of the metal are donating towards this end like this. So you can see one sigma bond and one pi bond has been formed here, correct? Okay. Okay. So this is how the acceptances would be. Now, this type of a bond, everybody, where you have a sigma bond and a pi bond forming. Listen, remember that pi bond must be the pi electrons must come from metal, while sigma electrons must come from ligand. So that is called as synergic bonding. Synergic bonding. Okay. Another example, if you have something, let's say iron. On iron, you have an empty, a d orbital which has electrons in it like this. Let's say there are two electrons here in the lobe, and it has an empty orbital to empty d orbital to which electrons are coming from carbon monoxide like this. Because of the pi bonds present, there will always have a pi star orbital also present on it like this. So there is a pi star orbital present like this. This is the way the pi star orbital looks like. Okay. So now you'll see there is a pi bonding forming from between these two. This is the pi bond which is forming, and there is a sigma bonding forming here. So in short, we write it like this. This side we will have carbon monoxide, and then there is like a double bond form which is pi and sigma. If you notice this kind of a representation, that means we are talking about synergic bonding. Synergic bond. Clear everyone? I hope you understood why it is called as pi acid, because it is accepting a pair of electrons in the form of pi bond from metal electrons. Got it? Another very important case in this case is Zeus salt. Okay. Formula of Zeus salt is potassium, platinum, trichloroethene, like this one. Okay. This is Zeus salt. Now, Zeus salt is having Pt connected with three chlorides here. That's a normal sigma bond. So it's a simple sigma donor here. But on the other hand, we have CH2 double bond CH2. So what it is doing is it is converting this pi bond into a sigma bond and trying to donate it to platinum. And top of that, it will also have pi star orbital present here like this. So this is a pi star orbital which is present on carbon. Okay. Now platinum will try to offer the bond from its orbitals to these two ends. So in short, it looks like this. So now this pi bond is completely turning out into, a bond like this here. This is a bond which is supporting. Okay. This is a bond which is like a sigma bond here. This is that sigma bond. Okay. So that entire pi bond is converted into sigma bond. And here the overlapping between these two orbitals are coming from the platinum's d orbital. So one electron here, and it will make a pi bond one on this side, pi bond one on this side like this. All right. So I hope you got an idea that how things are taking place in Zeus salt. Overall, it has negative charge on it. This is a very important classification when it comes to ligands. Next. Next one is hapticity. Hapticity is how many number of carbon atoms are involved during the donation of the electrons from ligand. When ligand is trying to donate the electrons, how many carbons present in that ligand are actually involved in the donation? That is called as hapticity. That is called as hapticity. Let me show you. The representation itself will make a lot of difference. For example, if I represent it like this, CH2 double bond CH, CH2 minus. This is allyl carb anion. This is allyl carb anion. Okay. If this is a representation given, which means you are expecting only one lone pair donation from here. So now this is acting like a monodentate, monodentate, and hence the denticity here, right? Denticity here is 1, correct? Denticity here is 1. And we usually write it as eta power 1. The 1 means what? That is only one carbon involved during the donation here. But if the same compound is written like this, and I give it this way, and then I will show that there is a connection towards metal like this, correct? Which means the entire minus which is present over the resonance stabilization of this molecule, that is connecting to the metal. So how many pairs we should count? Because this pair and this pi bond, both of them are in conjugation. So it connects from both the ends of the carbon here. So when the connection is shown this way, that means this time the denticity is 2, denticity is 2, and hapticity is 3 because the pi bonds are moving across 3 carbons. Got it? And coordination number, that is coordination number of allyl carb anion now, allyl carb anion in this case is 2 because it is donating 2 pairs of electrons to metal. Okay, sorry, coordination number of CMA, not anion, CMA, central metal atom is 2 in this case. Got it? This is what it meant by hapticity. Check out one more example here. Suppose if I have cyclopentadienyl double bond, I have a double bond here with a minus charge on this position. Okay. And let's say this is how the structure has been represented for us. So it's very simple. That means this carbon has a lone pair with a minus charge. It is donating. So hapticity is also 1. Denticity. Denticity is also 1. Coordination number contributed from that group is also 1. But if the same connection, right? If the same connection, if at all I give you in the form of hybrid structure, that is, this is how I'll give it to you, that this minus is now connecting towards metal like this. In that case, hapticity is 5 now because it is connecting over 5. Denticity is 3. Coordination number is also 3. So now this time it is acting like a tridentate. This time it is acting like a tridentate. Clear? One of such kind of compound, right, is having like this pentadienyl, cyclopentadienyl like this. Okay, and it is connected one above and one below like this. Iron is at the center, and here there is a resonance here. Here there is a resonance, and from minus and minus, one bond is coming from this end, the other bond is coming from this end like this. Okay. Now I know that the hapticity for this is 5. Here also hapticity is 5. Iron is +2 oxidation state in this case. Got it? So in this case, denticity is 3. In this case, denticity is 3. So now what is the coordination number of iron? Iron +2 coordination number is 6 because 3 are coming from the top, 3 are coming from the bottom. Okay. In fact, if you notice the molecule, you know how it looks like, right? It looks like this, where you have an electron density, right, coming from the upper orbitals of the carbon from the cyclopentadienyl and from the lower part of it like this. This is how it appears. All right. This is also called as sandwich complex. Sandwich complex, or its actual name is ferrocene. Just like kerosene, remember ferrocene. Ferrocene means with iron. Got it? Now, how do we usually represent it? This is how, when the molecular formula is given, it has to be written like this: Fe eta power 5 and C5H5. There are two of them. This is what meant by ferrocene. Okay, just a second. Make a note meanwhile. right? Everybody clear on that? Another one we have similar kind, which is called chromosine. That is chromium with eta power 6 C6H6. C6H6. So this is chromosine, right? So basically this time it is complete benzene making a sandwich form. These are all sandwich type of complexes where metal has been sandwiched by this entire pair of electrons like this one. So here it is, eta power 6, denticity is 3, denticity is 3, and coordination number of chromium is 6. Last example, you can see is like this. If you have been given minus here, structurally I gave you minus here, double bond, double bond, double bond, and double bond here, and then this time it is given as a ring here, minus and minus, and then I have a titanium here. So connections are being given from these four ends, from here, from here, from here, and from here. So how do we read it, everybody? From here, eta power 5 and denticity is 3. Here also we read it as eta power 5, denticity is 3, correct? While mm, mm, no, no, I'll take one thing. One of them I'll take it as only 1 minus, okay? Like this, okay? So here it is eta power 1, denticity is 1. Here also eta power 1, denticity is 1. Eta power 1, denticity 1. Denticity is 1. And lastly, here it is eta power 3, denticity is 3. So coordination number of titanium in this case is 6. So while writing the complex, this is how we write it. Titanium sigma. The sigma means only one connection. So eta power 1 is usually written as simply sigma. So sigma C5H5 is one of them, sorry, three of them, and uh, pi C5H5. If I write it, that means it is the hapticity in this case is 5. Okay. So this is a representation of that complex. So whenever you see this kind of a representation, you should directly be able to correlate that the coordination number is 6. Probably the structure is like this. Okay. So please check this out, everyone. Now, let me just finish this last part of it. What is the type of ligands? The last thing is the type of ligands is, sorry, not type of ligands, basically type of complexes. This is about type of complexes. It's not the classification of ligands, type of complexes. There are only two type of complexes when we write it down. So one is homoleptic, homoleptic complexes. Homoleptic complexes means all ligands are same. In this case, all ligands are same. The other one is heteroleptic complexes. Okay, so here ligands may be different. For instance, if you have cobalt NH3 6 SO4, okay, titanium sigma C5 H5, and pi C5 H5. This is thrice like this. or K3, Fe, CN6. These are all homoleptic. If you have even one ligand changed here, like NH3, Phi, and Cl, and then SO4, and this will become heteroleptic. Done. So these are the homoleptic and heteroleptic classification. Please note, everyone. So this is more like an introductory part of coordination compounds. That is, what are ligands, what is their main classification of ligands, and generally how do we represent various nomenclature when it comes to ligands. Okay. So the next class is all about the writing the IUPAC names, all the different type of names. What are the rules that are followed during the IUPAC names here? And based on that, what is the type of questions that are asked, like EN number and so on. There are different factors. That's a topic which we'll discuss in the next class. Okay.